Hey everyone, in this video we're going to talk about the fundamental theorem of calculus. So we're going to start with this function letting g of x be the integral from a to x of f of t dt. Now what does this function do? We know that the integral, now from the previous sections, we know that the integral represents the area between the curve and the x-axis from, in this case, a to x. We're used to seeing it as from a to b, but this is now the area under f of t, between f of t and the x-axis from a to x. So what does that look like? Because x is a variable, right? So x is moving. So let's sketch a graph to show you what that looks like. So essentially, if I have the area between the curve f of t and the x-axis, this shaded area, what I'm saying is that this is that integral, the integral from a to x. So this is g of x. So it's the integral from a to x, the area between a and x of f of t is giving me the height dt. But this x is not fixed, right? So I can move x over here. And then now the g of x is giving me the area between a and x of the area between the curve and the x-axis. So my x is changing, right? X can move. So what does this represent, really? So think about it. What if f of t was velocity function? Then what is the area given us? So suppose f of t is giving us the velocity of a runner at time t. Then what does g of x give us? So let's take a look at the area under the curve. So we have our function, that's the velocity of the runner at time t in meters per second, and then the time, say on the x-axis or the t-axis, is in seconds. So we want to see the between certain times, between a and x, right? But the time is changing, so x is moving along. But if I look at the area under the curve in the x-axis and think of it as the sum of all these little rectangles, the area of a rectangle is base times height. And so here, what does that look like? So our area, which is base times height, in our case is going to be base in seconds, right? Because the base is over here. So this is our delta x. So in seconds times the height. In what are units of height? The height is given by the function f of t, which is the velocity function, in meters per second. So what happens here? Our seconds can cancel. So the area is given as just meters. So the area then is given as the distance of the runner in meters. All right, so that helps us understand a little bit more about the area problem. We discussed this a couple sections ago, also the area problem, right? If I think of this, I'm graphing velocity, then the area, right? If this is the rate of change, then the area is just giving me the position. So in this case, the distance of the runner in meters. And so the reason I wanted to do that example is to understand the fundamental theorem of calculus part 1 a little better. So the fundamental theorem of calculus part 1 essentially tells us that if I take the derivative of the integrals, and this is usually abbreviated FTC, fundamental theorem of calculus, and I'm just going to put part 1 here because there is a part 2. Part 2 is the big one. So part 1 says that if I take the derivative of my g of x, which is really the integral from a to x of f of t dt, what should I get? So now, based on what we did here, right, we said that the area is the distance. So if the f of t is the velocity, right, then when I have this, the integral, this is the distance or position. So when I take the derivative, the derivative tells me to do the rate of change of, in this case, the position or the distance. What should I get? I'm going to get velocity, right? And so what the FTC part 1 tells us then is that when I take the derivative of the integral I get the velocity evaluated at x. So the velocity in terms of x. So notice that this is the distance in terms of t, but then when I take the derivative with respect to that top limit, my x, the x that is moving, I get the velocity in terms of x. So my t's are essentially gone. And that is because as we're taking the areas of those, right, as x moves, we're plugging them into that function. And so we end up with the velocity in terms of x. So let's try our first example. So here's our example. Let g of x be this function, the area between t squared plus 5 and the x-axis on the interval from 2 to x. So it's asking us to find g prime of x. So g prime of x is the derivative with respect to x of the integral 2 to x t squared plus 5 dt. So according to the fundamental theorem of calculus, when I take the derivative with respect to x, my variable up there of f of t dt, I just get f of x. So what is my function here? So my f of t is t squared plus 5. So I'm just going to get, instead of t, I'm going to get x. So this will be just x squared plus 5. And that's it. So it seems pretty simple, and it is. So let me show you the formal proof as to why is the derivative then just a function evaluated at x. So let's do a formal proof of that. So to prove that the derivative, right, of our function, the integral of a to x f of t dt is just f of x, we're going to use the definition of the derivative. Now remember from earlier in Calc 1 that the definition of the derivative, so g prime of x then is going to be the limit as h goes to 0 of what? Of g of x plus h minus g of x all over h. So using the definition of the derivative. So let's look at what that really means. So we know that g of x is the integral from a to x of f of t dt. So when I put this into my definition here, the limit as h goes to 0, then g of x plus h is what? That's going to be the integral from a to x plus h of f of t dt minus g of x, the integral from a to just x of f of t dt, all over h. Now let's bring in a graph to show what does this mean, because remember the integral is given as an area. So I have two areas here that are being subtracted. So let's look at this in a visual sense. So let's look at the first area. So from a to x plus h. So if I put a here, then I'm looking at the area between a and say my x plus h is over here. So we're looking at this area. So that whole area is represented by this integral, right? Does that make sense? So this whole thing is the first integral. So that is the area from a to x plus h. Now what about the second integral? Which area is that? So what about this area? That's the area just from a to x under the curve, between the curve and the x-axis. So we don't know how big h is, but so let's say that my x is here. Then this area, right, is the area from a to h. So I have this area here. So since I'm subtracting them, so what am I left with in here? We're left with just the area between x to x plus h, right? So when I take the blue area and subtract the green area, I'm left with this guy. So the area just from x to x plus h. So we can write that in our definition then. Then this is limit as h goes to 0 of, how do I represent the area from x to x plus h? So that's going to be then just the integral from x to x plus h of f of t dt. But remember, this I drew it kind of large. So let me see if I can adjust that. So because h technically is supposed to be really small, right? So let me move my green area just a tad bit more closer to the x plus h. So that then when I take the difference in those areas, so what I have here then is I'm just left with this tiny sliver of area. So that is really my area from x to x plus h, this tiny little sliver, right? H is supposed to be small. So I'm left with that and then divided by h over here, but this is just a sliver, so it's really just a rectangle. What's the area of a rectangle? Right, this is, what's the distance from x to x plus h? That's just, so my delta x there will be just x plus h minus x, which is just h, and the height is, what is my height? It will be the f of x, right? Because I'm using this, so this will be when I'm at x, this is x over here, that is f of x. So this I can rewrite it as, so then g prime of x is really equal to the area of that rectangle. So as the limit as h goes to 0, the area of this area is really the area of that piece of that rectangle, which is the base times the height. The base is h and the height is f of x divided by h. And notice what happens here. My h's cancel and I'm left with just f of x. So therefore the derivative is equal to just f of x. And so that proves our FTC part 1, which just tells us that the derivative of the integral is just f of x. So let's try the second example that I had prepared for you. So this we can box it up, put it in a note card, something that will help you remember it. And let's try the second and third examples. So for this example, find the derivative of the integral from 17 to x of cosine t minus sine t dt. So the derivative of an integral, I just essentially get my f of whatever my function is in terms of x. So our function is the stuff on the inside. So then I can say here, f of t is equal to cosine of t minus sine t. So therefore, the derivative of this integral from a to x, 17 to x of cosine t minus sine t dt is going to be what? It's just going to be cosine x minus sine x. And that's it. And really the real work here is done in this proof. But then we don't have to reinvent the wheel every time. We just know, okay, well, the derivative of the integral is just a function. And so we can do it really quickly. The only problem is when we have chain rule. So when we have, so in example 3, so in this example, we have to use the chain rule. Why do I need to use the chain rule? Because I have 5 to x squared. So it's not just x. Right? The fundamental theorem of calculus just says if it's from a to x, so if you have a constant here, from a to x of f of t dt, then you get f of x. But here, it's really what we have going on here is that you have g of x is essentially, it's not really g of x, you have g of some other function, g of h of x, when you have your x squared there. So how do you find the derivative of that? So the derivative of g of h of x then will have to be by chain rule, the derivative of the outside, the inside left alone, and then times the derivative of the inside, times h prime of x. So in this case, our h of x is x squared. So when I take the derivative here, So when I have d dx of the integral from 5 to x squared of 3t minus e to the t dt, I'm going to have the derivative of g prime of h of x, so that will be just my f of x squared, my f of h squared, right? So in this case, it will be 3x squared. So instead of t, it will be x squared minus e to the x squared, but then by chain rule times the derivative of x squared. So that will give me, so I get my 3x squared minus ex squared times 2x. So whatever you have in there, if it's not just x, you essentially do the same thing. You do your f of whatever that is, but then times the derivative of the exponent. Some other things that you might see is, what if I have find the derivative of something like the integral of x and then to say sine x of t squared plus 1 dt. Now notice that the FTC here does not apply because I don't have just a constant. So one thing you could do is find a place in between x and sine x where you can split it up and go to a constant. Both of them have a domain that is all real numbers, so you can really just choose any value that is in the domain of both of them. So I can say find the derivative then of the integral from x to 0 of t squared plus 1 dt, and then plus the integral from 0 to sine x of t squared plus 1 dt. And now I can use FTC part 1 on this side and FTC part 1 on this one as well. So that's something to keep in mind when you have the double x's in there. You can split them up, keeping in mind the domain of each of the functions. All right, email me if you have any questions. Next video, we'll do FTC part 2, which is the big one.